Hello and welcome to Romeca Corporation's three-part tutorial on how to drive a conveyor motor with a VFD. In this series, we'll discuss how to use a variable frequency drive to modify conveyor belt speeds without damaging the drive motor. You'll learn how to verify VFD conveyor drive system adequacy by checking required power versus available power and motor cooling capability, if applicable, at all relevant rates. This is part 3 of our three-part tutorial on how to drive a conveyor motor with a VFD. In this session, we'll demonstrate how to set VFD frequencies to avoid mechanical overstress of conveyor drive motors and how to avoid inadequate motor cooling. To watch any of the other videos in this series, click on the link in the upper right-hand corner of your monitor anytime during this video. Now let's talk for a couple of minutes about variable frequency drives. What are they and what do they do? A variable frequency drive is a frequency converter. It uses pulse width modulation to change power supply frequency. The whole point is that we want to be able to vary belt speed by changing the power supply frequency. Note also that a VFD has the ability to drive a three-phase motor while running on a single-phase power supply. Motor torque, as long as the frequency setting is within an allowable spectrum, is more or less 95% or more. So we could consider, for the purposes of this discussion, the torque is going to be constant as long as we restrict ourselves to an appropriate frequency spectrum. Years ago, we used to say that the frequency spectrum needs to be restricted between 12 Hz and 66. However, nowadays, with flux vector VFDs being very common, we know that we can extend the spectrum beyond the old 12 to 66. In fact, we can go slower than 12 Hz and we can go somewhat higher than 66 Hz. But you need to check with the VFD manufacturer before you do that. It's important to adhere to these two warnings. If the VFD frequency setting is too slow, you might have poor fan cooling or poor oil cooling, or conceivably you could have the setting too fast, which would also result in poor oil cooling. I'll explain in a minute. First, a quick look at pulse width modulation. Pulse width modulation is the term we use when we want to refer to how a voltage source is being modulated as a series of on-off pulses electronically. These on-off pulses control the amount of current, the amount of average current, which flows in the conductor during each pulse. And the voltage pulses are shown in blue as rectangles, if you will. Some are broad, some are narrow. And the induced waveform, which has a sinusoidal pattern, is in red. And that's attempting to depict what the AC frequency, the AC current frequency would look like. The higher the clock frequency that's built into the VFD, the smoother is the waveform. VFDs can have clock frequencies from as low as a few kilohertz to as high as a few megahertz. Now let's look at the important phenomenon in which we know that current draw and power provided by an AC squirrel cage induction motor are linearly proportional. Here we see on this graph 4 different models of a certain type of conveyor drive. Second from the left, you see the 10 horsepower bar. So 10 horsepower is available, and as a matter of fact, it matches the photo that I showed previously. So this is a 10 horsepower AC squirrel cage induction motor, which draws 12.1 amps at full load on a power supply of 460 volt, 3-phase, 60 Hertz. We also have a 20 horsepower model available. And as you can see, 20 horsepower is available. However, the FLA would be 23.6. So the stator would be designed to continuously carry 23.6 amps while the motor is running continuously, indefinitely at full load. Now watch this. If a 10 horsepower motor is subjected to a situation in which required mechanical power is 20 horsepower, it's going to attempt to draw 23.6 full load amps, and therefore it's going to burn. To prevent this, an external overcurrent switch would prevent current from flowing higher than 12.1 full load amps. If that external protection is not provided, then the failure that you see on the right would occur. A 10 horsepower motor left unchecked will attempt to provide 20 horsepower by drawing more and more and more current through the stator. Let's look again at the 4 examples I gave previously. These are 4 different power examples. We'll compare required and available power at a design rate and an installed power supply, and then we'll check required and available power at all relevant rates. So in the continuous case, we called it conveyor A. You remember that we set the power supply at the supply as it comes from the power company. 460 volt, 3-phase, 60 hertz. We selected a 25 horsepower motor to move the conveyor at 330 feet per minute. 25 horsepower was more than the 23.6 horsepower that was required. In fact, we actually calculated the belt pull of 2,360 pounds, and we know the product of belt pull and belt speed gives us 23.6. In the B case, we had a failure. The reason we had a failure was we calculated belt pull at 4,060 pounds. We have the slower belt speed of 165. The product of those two numbers divided by 33,000 is 20.3 horsepower. Now we've installed a 25 horsepower motor. At first glance, you might think you have enough power installed. However, when the power supply with a VFD is changed to 460 volt 3-phase 30 hertz, the available power is linearly proportional to the frequency. So since it was designed to run at 60 hertz and provide 25 horsepower, at 30 hertz, it's going to provide 1/2 of 25 horsepower. Required power exceeds available power, and that would be a failure. Now, what do? This is on the left-hand side. We're looking at the failure case of conveyor B. On the right, you'll see what we suggest as the solution to the problem. We need to install a 50 horsepower motor designed to run at 460 volt 3-phase 60 hertz. And we use the VFD to adjust the frequency to 30 hertz. A 50 horsepower motor designed to run at 60 hertz, when running at 30 hertz, will provide 25 horsepower. Therefore, 25 horsepower is higher than 20.3. In this situation would be successful. Note, however, it's very necessary to double check the A case. Now we go back and we check the faster belt speed. This was the original design setup, which worked. Let's look at the new setup and make sure that it also works. Now we have a 50 horsepower motor designed to run at 460 volt 3-phase 60 hertz, and we're going to provide it with 460 volt 3-phase 60 hertz. Therefore, we have installed a 50 horsepower motor. We have available to us a 50 horsepower motor. 50 horsepower exceeds 23.6, and we have a successful application. Now let's have a look at the 2 metered cases. In the A case, we had a 50 foot per minute belt speed and a material handling rate of 400 tons per hour. I told you before we calculated separately what the required power is. In actual fact, the belt pull requirement is 10,164 pounds. At a design belt speed of 50 feet per minute, we know that 15.4 horsepower is required. Now in the A case, we're going to install a 20 horsepower motor designed to run on a supply of 460 volt 3-phase 60 hertz. And just in this example, let's assume we have an 8-pole motor, and you know what that means. And let's assume we have a 2-foot diameter pulley, and you know what that means. And let's say that the supply is what I just said, 460 volt, 3-phase, 60 hertz. Available power is 20 horsepower. 20 horsepower is larger than 15.4 horsepower, therefore we have a successful application. Now let's see why the faster belt was a failure. You'll remember we wanted to increase the belt speed to 100 feet per minute by increasing the power supply frequency to 120 hertz. This is impossible. We want to get 800 tons per hour by speeding up the belt, so we were tempted to crank up the VFD to a faster frequency. We've calculated separately that the belt pull required to move 800 tons per hour at 100 feet per minute is 9,867 pounds. Multiplying belt pull and belt speed, you can see that 29.9 horsepower is required. We've installed a 20 horsepower motor designed to run on 460 volt 3-phase 60 hertz power supply. An 8-pole motor will have a rotor speed of 900 RPM at 60 hertz. A 2-foot diameter pulley, which we're using in this example, will have a rotor torque requirement of 116 will have a gear reduction of 113 to 1. We calculated the RPM of the pulley, we know the RPM of the motor, we can calculate the gear reduction, and that tells us that rotor torque will be 116.7 pounds. It's impossible to attempt to have this motor run at 120 hertz because 116.7 foot-pounds of torque at the motor is not available at 120 hertz. We cannot use the same ratio as we did previously when we cut a frequency in half. We can't double the frequency because, take a look, if we say the motor rotor torque is 116.7, which it isn't, but we say it is, we assume it might be, we divide 120 by 60, multiply by the RPM, multiply by 2 pi per rev, and this implies that the motor is 1.3 million foot-pounds per minute, which is impossible. That's 40 horsepower. It's impossible because the motor will burn. It cannot carry the required current to provide 40 horsepower. It's designed to carry the current to provide 20 horsepower. Let's see how to solve the problem. This is what we started with. This is the failure case. Let's see how to solve this problem. We're going to install a new motor, and we'll install a 40 horsepower motor designed to run at 460 volt 3-phase 60 hertz. Now, if we run that motor at 460 volt 3-phase 60 hertz, we will have an installed power of 40 horse, and we'll have an available motor power of 40 horse. Therefore, the 40 horsepower drive is more powerful than the required 29.9, and we have a success. Now let's go back and check A and make sure that that works. You remember now that we have a 40 horsepower motor designed to run at 60 hertz. We need to decrease the speed to 50 feet per minute from 100 feet per minute, and we're going to do that by using the variable frequency drive to cut the frequency in half. A 40 horsepower motor designed to run at 60 hertz. When we run at 30 hertz, we know that the available power will be 20 horsepower. Since required power calculated separately is 15.4, and since 20 horsepower is higher than 15.4 horsepower, we have a success. Let's summarize our solutions to the previous 4 cases. In the continuous conveyor case, a 25 horsepower motor originally installed to provide 25 horsepower at 60 hertz could not provide 20.3 horsepower at 30 hertz because available power was limited to 12.5 horsepower. We solved the problem by installing a 50 horsepower drive system designed to provide 50 horsepower at 60 hertz. Therefore, available power when running the drive at 60 hertz was 50 horsepower, and available power when running the drive at 30 hertz was 25 horsepower. Power is now adequate in each case. Available power is now adequate in each case. Here's a tip when evaluating drives at 2 extremes of speed. Size the drive at the high speed first, and then check the adequacy at the slower speed. In the metered conveyor case, a 20 horsepower motor originally installed to provide 20 horsepower at 60 Hertz, could not provide 29.9 horsepower at 120 Hertz because available power was limited to 20 horsepower. We solved this problem by installing a 40 horsepower drive system designed to provide 40 horsepower at 60 Hertz. Therefore, available power when running the drive at 60 Hertz was 40 horsepower, and available power when running the drive at 30 Hertz was 20 horsepower. Available power is now adequate in each case. Did we have a race car installed but needed a truck when the speed was changed? Or vice versa? I'll let you decide. Now let's discuss the topic of motor cooling. We need to verify that heat dissipation capability is correct for the installed motor at the installed power supply, and we need to double check that heat dissipation capability is available at all relevant rates. Here's the case we looked at in the first video in this tutorial. You can see that a totally enclosed fan-cooled motor has been installed to drive a conveyor. A totally enclosed fan-cooled motor uses a fan which is enclosed in a shroud, which pulls ambient air across cooling fins so as to dissipate the stator heat into the ambient air as it's pulled across the outer surface of the motor. This symbolizes how a motor may be installed to run at its design frequency. So a certain amount of air, measured in CFM, should pass over the fins. Let's say we install a variable frequency drive, drawing air too slowly over the fins. There's a possibility that if the fan is too slow, it will now pull enough air across the fins to adequately dissipate heat from the stator. Now let's have a look at a motorized pulley. A motorized pulley encloses the motor and the gearbox within the pulley shell, as you can see pictured here. Rather than using air to cool the motor, internal oil is used to transfer heat from the stator into the puddle of oil at the bottom of the pulley, transferring heat from the stator through the pulley shell and into the belt. We use the belt as an infinite heat sink. So when a motor has been designed to run at its power supply frequency, we anticipate that a certain quantity of oil will flow over the stator, pulling heat over the stator and into the oil at the bottom of the pulley. If the motor is too slow, it's possible that we could compromise the oil cooling system and not pull enough oil over the stator to properly cool it. So therefore, are we taking our race car and trying to turn it into a truck by having the motor turn too slowly? The alternative is, what happens if we take our motorized pulley and attempt to make it spin too fast? We could have a situation in which centrifugal force keeps oil from even touching the stator, in which case the stator would be too hot. So have we taken our conveyor drive and attempted to turn it into a race car, having it perform too quickly for the oil cooling system to function? That concludes part 3 of how to drive a conveyor motor with a VFD. We learned how to set VFD frequencies to avoid mechanical overstress of conveyor drive motors and how to avoid inadequate motor cooling. This 3-part tutorial has covered an introduction to the topic of correctly driving conveyor belts with VFDs, an exploration of all relevant rates, an exploration of all relevant powers, and an explanation of how to set VFD frequencies to avoid motor damage. We hope you found this short tutorial useful. To watch any of the other videos in this series, click one of the links at the bottom of your monitor. To go to our website, click the link in the upper right-hand corner of your monitor now. Thanks very much for watching.